Hey everyone, welcome back to the series. And in this part, I'm going to talk about the computational scaling, what it really means, and why it's important in the world of generative AI and agent-based systems. So when I talk about computational scaling, I mean the boosting and optimizing the compute power to handle the growing demands. But we have to do it in a way that's still efficient and cost effective. And it's not about adding more machines or bigger GPUs or powerful GPUs. It's about scaling smartly to keep things running smoothly as our AI systems grow more advanced. So why this matters so much? First, the resource pressure is very huge, and training and running these AI models now requires massive computational resources, especially when you were simulating real-world environments or working with complex agent-based systems. And as these environments get more sophisticated, the cost of running them skyrockets. Then second, we have the data problem. AI models need to process fast changing, diverse data sets often in real time. And that's not easy. Scaling data collection and the processing can become a serious bottleneck. And there's always a risk of AI generated content contaminating the future decisions. Third, we have the size versus speed challenge. So bigger models are powerful, but they can sometimes slow you down. In the real world, you need smaller and more efficient models that can deliver quick results without wasting, much resources. And then we have these simulations. These are getting very heavier. If you are training model that interact with the dynamic real world environments, you need high compute power and super low latency hardware, right? And your simulations have to be scalable and accurate as well. And then lastly, we have the coordination problem. So when you have this multiple agents and models working together, managing that complexity across the distributed system is a very serious challenge, and it demands robust and scalable compute infrastructure. So, what's the way forward? You're probably wondering what should we do. Well, to navigate all this, we easily follow three core strategies. One is scaling up to maximize the raw computing power, and then we will also discuss about scaling down to make models faster and leaner and more efficient. And then we also have the scaling out to build flexible distributed AI ecosystem that can handle complex and multiple agent tasks. All right, now let's talk about the first scaling strategy, which is the scaling up. So when you scale up, the idea is to grow. We increase the model size, train on larger data sets, and invest some, more in computing power to build stronger or more capable AI systems. And this is the part we have already seen with models like GPT-3 to GPT-4, and now we have GPT 4.1. You can see the image over time. We have bigger LLMs or larger LLMs in terms of parameters and all, and the training time has increased exponentially, requiring huge computational power. The main benefits, if you ask, like these models can handle wider variety of tasks and tend to generalize well across different domains. But of course, it's not as simple as the bigger is better. So one of the biggest challenges here is the data saturation. So what we say, we are starting to run out of fresh, high quality training data, and as a result, teams are relying more on synthetic data or lower quality data sets, and that brings its own risk. Um, like there is no model limit, there is also some model limitations. The models grow, but they can become bloated or redundant and harder to understand, and sometimes making them bigger doesn't actually make them smarter. And of course the compute costs are big blocker. So training and running these large models can get incredibly expensive and energy hungry, so this can make them hard to sustain, and especially in production. So if you ask, like, where is this heading, the industry is shifting toward smarter data sets, focusing on the quality and diversity and domain specific training rather than just adding more data. So we are also seeing there is a push between um, or a push toward a more efficient training setups, using distributed systems and smarter optimization to save resources. And there's a growing trend in dynamic inference where the amount of compute can be adjusted based on how hard and complex the task is. Is it always using the maximum power? So if you were asking about the like how do you want to scale up, here for a few practical tips. You should always focus on scaling what really matters to your client or your specific use case. Not every problem needs to be have the largest model or even generative AI. Then embrace synthetic data and smart data collection to overcome the data bottlenecks. That is very important. And then you also have to build systems that are flexible, that can scale up, scale down, or scale out whenever it is needed. And lastly, always design with sustainability in mind. Both environmental cost and operational cost should be part of the conversation from the start. So now let's shift gears and talk about scaling down. Scaling down is all about making models smaller, faster, and more efficient without losing the performance we care about. The idea is to really focus on what's essential. We carefully strip away parts of the model that aren't needed to keep only pieces that actually drive the results. And there are a few great techniques to make this happen. Things like pruning, quantization, knowledge explanation. You have probably heard of it while we discussed in DeepSeek R3 or R1. Yeah, so DeepSeek V3 and R1. And we also have low rank adaptation. You can see in the image that smaller models show great MMLE scores. Not great, but it's quite impressive. So this help reduce the size and compute demands of the model, and in return we get faster responses, lower latency, and less energy use, which is very important. Pretty useful, especially for edge devices or mobile setups, but it's not without challenges, right? So when you start cutting down a model, you can you can run the risk of accidentally removing something important, and it's a fine balance, making the model smaller while still keeping it smart enough to do the job well. Another issue is figuring out exactly which parts to remove and which parts to keep. That's actually pretty tough to automate, and it's not just about shrinking the model; it's about shrinking it the right way. So what's the future of scaling down? The trend, if we are talking about the trend, we are heading towards small and fine-tuned models that are specified for very specific tasks, like domain specific. And to make up for what they don't know, we can pair with external systems like retrieval augmented generation or RAG, which can help fetch the right information in real time. We are also seeing the rise of hybrid architectures where smaller core models can plug into larger and dynamic systems whenever it is needed. Here are some practical tips if you are thinking about scaling down. Use smart compression and retrieval based model or methods to keep your models light but powerful, and make sure your infrastructure is cost efficient. Think about auto scaling, batching, and even smart GPU usage to save resources. And always keep an eye on token usage and latency, especially in production. So you can make sure your model is still delivering very value quickly. Scaling down is a great strategy when you need speed and cost efficiency or age deployment, but sometimes you will want to combine smaller models into larger ecosystems, and that's where we will talk about scaling out. Now let's talk about scaling out, which is one of the most exciting directions in the world of generative AI currently. So far, we have looked at building bigger models and shrinking them down. Scaling out is a different mindset. So instead of focusing on the large model, we create an interconnected ecosystem of smaller and specialized models that can work together. And this is often called the AI ecosystem strategy. It's about deploying multiple lightweight models, each focused on specific tasks, and connecting them together modular, through modular and reusable interfaces. It's super flexible and allows us to cover more real world scenarios without overloading in a single model. We can also use model fine tuning techniques like LoRa and adapters to quickly update and customize parts of these models with minimal resources. And one of the best parts is like seamless integration. So with scaling out, you can connect models, agents, and devices across different platforms, whether that's in the cloud or in any edge devices or across the distributed ecosystem. Plus, the approach makes built-in privacy much more achievable. Um, Using techniques like federated learning, we can train models without sharing raw data, which is a big win for security and compliance. But of course, there are challenges. So coordinating these lots of smaller models can introduce delays and system overhead. Designing clean, reusable interfaces and taking careful planning and extra effort. And also, when you are working across distributed systems, you can also you also reduce the data fragmentation, drift, and inconsistencies. And with even more open and connected systems, security and trust become very hard to manage. We are moving towards the AI marketplaces and model stores, where you can easily share, customize, and deploy models. And there is also a growing focus on real-time collaboration between AI agents at the edge, so devices can work together and without always depending on the cloud. And we are starting to see the condition control models that can adjust dynamically based on the task of the user's needs. And scaling out is all about flexibility, adaptability, and building systems that can grow in different directions. It's complex, but if you do it right, it opens up huge possibilities for scalable, efficient AI. um, let's talk about some practical tips. First, focus on building the modular and specialized models. Don't try to create one huge model that does everything. Instead, design smaller task-specific models with clear, standardized interfaces so that they can work easily together and be updated whenever needed. Second, use strong orchestration tools. So when you are managing multiple models or agents, you need solid orchestration to handle the coordination, load balancing, and multi-agent workflows without getting stuck in bottlenecks. And then third, make edge and distributed learning a priority. Support deployments and leverage federated learning to reduce the need of constantly move data forward. This will not only speed up things, but also to make sure your systems are more privacy friendly and responsive. And finally, baking security and governance from the very beginning. It's very crucial to build proper monitoring, security, and compliance checks across all over the models, agents, and systems right from the start. And it's much harder to fix things later. If you get these four things right, scaling out can be powerful and sustainable way to grow your generative AI system. um, Now we will talk about quick comparison between scaling up, scaling down, and scaling out. Your approach, I mean, whatever you take, like I said, scaling up, down, or out, each approach has its own trade-offs, and the right choice really depends on what you are trying to achieve. If you scale up, you will get top tier performance and accuracy, but it's expensive and also energy hungry and usually slower down the response. It works well when you need a very high accuracy for low volume use cases. And then we have scale down. You get fast, efficient models that are easier to deploy, especially on edge devices. It's cost effective, but you can lose some accuracy if you cut too much. And it's great for lightweight, cost sensitive applications. And lastly, like I said, like if you have scale out, you can build powerful, flexible AI systems with multiple smaller models working together. It offers high performance if done well. Remember, if you are do well, then it is great, but you need to do good orchestration and strong infrastructure to make it work. This is the perfect to for large scale, high volume systems. Each path comes with strengths and challenges. Probably you have understood by now. And it's less about picking the best method. It's about choosing what fits your system and your resources, your business goals. And anyway, that being said, I will just end the video here and see you in the next part, where I will continue this computational scaling for the hardware requirements, also the storage and retention policy, and then we will go forward. Thank you so much for watching.